So this is the first video for Light, chapter 16, and we're going to start out by talking about light and its characteristics. The second part kind of focused around polarization and color that we'll see on part B. So if you can get your PowerPoint out, I think you probably have those. Be a good idea to look at that as you go and maybe add some notes on. First item of business is that we're going to talk about the general characteristics of light. Light is a transverse wave, but it's a little different than the ones we've talked about before because it has two parts, and one of them is an electric function or electric part, and the other is a magnetic part. And just like when you put a copper wire into a magnet, if you can move the wire through a magnetic field, you produce electricity. Well, it's the same here, that as the magnetic part of the wave increases, so does the electric part of the wave. So the electric and magnetic part are at right angles to each other, as you can see here, and they have a common vector that travels through the center point, and that is the ray of light that travels through space. Like before, we represent wavelength with lambda, which looks like the upside down Y. Yours isn't in color like this, but you see that the sideways is the magnetic and the up and down is the electric. That doesn't matter three-dimensionally. If it turns around, it's different. So, all right, we'll move on. So we're going to talk about the ray model of light. Light travels in straight lines until it encounters a boundary. At that point, it can either be absorbed, refracted, or reflected, or some combination of the above. So those are the three choices. Absorbed means that the energy is soaked up by the material and converted to either heat or internal energy. If it's refracted, think about out on the beach. You're running out into the ocean. As you run out in the ocean, let's say there's a family running out. The family runs out. You're not going to be able to run in a straight line because it's hard to run in a straight line when the waves are hitting you and everything. Light's the same way. When it goes from one medium to another, it changes speed, and as it changes speed, it bends. We call this bending refracting. Kind of like the family, the big waves, like the red waves, are not affected as much as the little waves, which are affected more. That is what causes the light to be spread out as it goes through a prism or maybe through a vase in the window. Anything that will bend light bends the different colors differently. That bending of different colors is called dispersion. I don't have that in the notes up there. They didn't have that in the chapter, but you should write that down. Dispersion is the spreading of colors differently as they're diffracted. Objects such as the sun or light bulbs or any source of light are called luminous sources because they produce their own light. Objects that reflect light are not luminous sources. They just take the light that some other object produces, kind of like the moon. The moon doesn't produce its own light. It reflects light. Looks bright to us, but that's just the sunlight's light that's being reflected off of it. So light and matter. Three main types of matter when it comes to light passing through it. Opaque would be that light doesn't pass through. If we had, say, black paper on the window, couldn't see through that because it's opaque. Translucent. The lights that are up above in your room, they're translucent. You can't really see what's behind there, but light is transmitted. And the problem is that, and it's by the nature, they don't want the light to come out sharp with shadows. They want it to be diffused in all directions. So you can see kind of the crisscross pattern on the lights that it causes the light to be bent in different ways. Third, transparent objects, they pass clear images. Sometimes they will bend the image a little bit as they pass it, but they do pass the image as it is. You can see the image clearly. So those are the three main types, ways we classify matter based upon how light passes through. So just like with sound, we're going to quantify light. The rate at which light source produces light is called luminous flux. The luminous flux, we use the letter P to stand for that. I understand. We'll also use that for power. So, you have to kind of look at the context of the equation to see which one we're using. We won't be using power in this chapter like we did in last chapter, so it shouldn't be confusing. The luminous flux falling on a given surface, not what's produced, but what's falling on a surface, and that varies with distance, is called a luminance. Luminance is the inverse relationship with the square of the distance. So if you have a distance of 1 meter compared to 2 meters, then think of this. 1 over 1 squared is 1. 1 over 2 squared would be 1/4. So basically 1/4 of the illumination at 2 meters. 1/9 of the illumination out at 3 meters. So when you're comparing the different illuminances. So decreases with the square of the distance. And there's an example on the next screen that you can see that. So you can see the inverse square of illuminance, inverse square law, E, illuminance, equals 1 over d squared, where I is the intensity, is I over d squared. I is the intensity and d is the distance. So, if you want to use a standard equation just to kind of compare, you can plug 1 in for I. But basically, our equation is that as you can see, as you get further and further out, the light is spread out, and when it's spread out, it's going to be dimmer. So the inverse square of the distance tells you how much dimmer it's going to be than other distances. Luminous intensity is measured in units called candelas, and some of these words you want to maybe put on flashcards or highlight on your notes. Luminous intensity is luminous flux divided by 4 pi. If two sources have the same luminous intensity, a source at twice the radius would have 1/4 the luminance on a screen. So again, an inverse property, the further out you get, the dimmer it is. That should make good logical sense. So surface illumination, the luminance caused by a point light source is represented by the following equation. This is an equation that you'll have. Point source illuminance, so that means the actual illuminance by that. When we say point source, just think of one dot of light, done so for calculation's sake, because if the bulb were a big bulb, then obviously there would be some issue about is it measured from the surface of the bulb or from the inside of the bulb. So we call it a point source and consider the very center of the light source as being that point of origin. So that formula is one that you'll be given. E equals P over 4 pi r squared. This should look a lot familiar to the equation that we had in the sound chapter. Remember, P in the sound chapter was power in watts, where here it's not. So we're not going to have to be, we won't be confused with the watts in this chapter. They won't be used in this same context. So the speed of light is constant in a given medium. If we look at the speed of light from what we're going to use the speed of light in ways we're going to use it, we use the variable c to represent speed of light. And for our sake, 3.00 times 10 to the 8 meters per second. that would be very, very, very fast, so around 7 times around the world if it were able to go around in a circle in a second. First person to measure light between any two spots was Danish astronomer Ole Romer, and he measured the speed of light not as accurately as we have it today. I'd say that as far as our actual speed of light and who we give credit to, our current actual value would be Albert Michelson, and he measured between two peaks in California, 35 kilometers apart. He measured the travel of light as it went over and back, and he actually gave us a fairly good measurement compared to the value that we have today. So he's the one that's given credit for that first accurate measurement. So we'll finish up with a couple of formulas. And first formula should look familiar to you. C equals F lambda, which in last chapter we used V equals F lambda. Same thing, because C is the speed of light. V was the speed of sound. And in this case, unless you're given a speed of light, remember it changes in different media, just like you running on a track or you running out in the ocean changes depending on what medium you're in. The value for C will be given on your possibly useful page as 3.00 times 10 to the 8th meters per second. So in most cases you'll use that. So if we're not solving for that speed of light, what are we solving for? Well, for the most part here you're going to be given a frequency and you'll solve for wavelength, or you'll be given a wavelength and you solve for frequency. So same process algebraically that we did last chapter, so that shouldn't be anything new. Also want you to be able, if I give you, of course you're going to get the speed of light, I want you to be able to use dimensional analysis in order to solve for how far light would go in an hour, or how far light would go in a day or a week. You'll have a problem like that on your review, on your quiz, on your test. Just a good review of dimensional analysis. Make sure that you've got a handle on how to do that. If you've learned that in chemistry, which you should have, this should be nothing new. It should just be a little bit of a review. So that's where we're going to stop today. The second set of notes will go on and talk about color and polarization, and how we see color and how colors blend together. So work on your review some, read through the chapter, and we will see you next time. Good luck.